All right, and the length of the tube is L. And apparently there's some block waiting out here to accept the dart. And it has mass capital M, and the dart has mass lowercase m. So look familiar to you guys? It should look familiar to about 44 of you. Of course, we know there's several that does not look familiar to, but I won't lament that. So it's a constant force F. Here's where I have to back up all the things we've been planning this year. This year they've been really adamant about word count being high. And now all of a sudden word count is not high. So every word has become important. This is a fairly straightforward sentence, but every word has value. A constant force F is exerted on a dart of mass m in the horizontal direction as it moves through a tube of length L. After exiting the tube, the dart collides with the box that sits at rest on a table with a coefficient of friction of mu k. The dart block system then slides across the table and comes to rest after traveling a distance d. So there's a lot there. The picture doesn't show you all the pieces, and that's okay. In your head, you got to keep track of those pieces, or if you're like me, I tend to like to have a bit of a visual. So now that I know what's going on, I know, okay, this is really just part A of the problem. And after this, there's several other things that are going to happen. There's going to have to be this moment when the dart collides with the block. This instantaneous collision. Made the block too big. There we go. That instantaneous collision that occurs, where the block and the dart become one and now have some combined velocity v. I'm going to need another letter for that in a minute, but I'm just going to say v for this second. And then there's going to be this longer term thing where after the collision, which occurred here, the block and the dart slid some distance. And they say I'm supposed to use d. Now the dart kind of hanging out the back here of this block, and the dart and the block have slid d. But now the velocity here is 0. So now I have kind of a portrayal of what the whole problem is like. And I can section it off to think about what might be happening between each section and at that instant. So I don't know what the questions are. All I'm trying to do is, in my head, put together the things that they've told me. And they've added a few things that, into this too. They've told me that the dart's experiencing a force F and that it is constant. That's important because that automatically changes some things about the system in my head. A constant force means that the work done is just the product of force and distance. That's useful to me. It means that there's a constant acceleration. So that means motion equations are available to me. All of those little things are the kinds of things that should be on your notepad, that are on that special sheet you're making. That what is the implication of saying an object is experiencing a constant force? And there's several implications there. So I'm going to take a minute and say them again because I think it's important that you have them. First, the moment we hear constant force, it means constant acceleration. That means Galileo's motions equations. They're available. Next, when we have a constant force, if it's constant through a distance, then work is just the product of force and distance. If it's constant for a time, that means the impulse is the product of force times time. Those have implications too. If I know net work, I know change in kinetic energy. If I know impulse, I know change in momentum. So when we talked about the flow chart, this is a flow chart. Is the force on the object constant? Yes. All right. Every one of these next things is true because of it. So, like I said, I haven't looked at the question yet. It's not exactly true, but you know. All right, so A, students experiment with a variety of tubes. Yes, because there's all sorts of tubes laying around. Assuming that air resistance is negligible and that all other parts of the experiment remain the same, should the students use a long tube, a short tube? What? Should the students use a long tube or a short tube? I'm sorry, maybe Mr. Shelton can't read anymore. Students experiment with a variety of tubes. Assuming that air resistance is negligible and that all other parts of the experiment remain the same, should the students use a long tube or a short tube, make the stopping distance the longest? So we can see that there was not a lot of editing done here. So I'm going to assume that the sentence was supposed to say, should the students use a long tube or a short tube to make the stopping distance D the longest, and justify your answer. Let's work this out. Now, if you wrote, and look, I read like 6 of the answers that people wrote. That's not many, but it's amazing the number of people who simply wrote they should use the long tube and walked away. I want you to look at what I've written here. Saying the tube is long or saying the tube is short affects only what happens at the tube. If your answer doesn't address all of the parts of the problem to where D changes, then your answer is wrong. They gave 4 points for this. 4 points. So when you say, what's going to make the stopping distance the longest, you have to indicate everything that would contribute to why the distance would change. For example, what is when the dart hits the block here in the middle? The dart and block now have velocity. When the dart and block are being brought to rest, what's causing the dart and block to be brought to rest? All right, so the work done by friction. Now, this part's important. Is the frictional force any different if the tube is longer? It's a yes or no question, so maybe I'll take that answer in the participant window. And let me erase that there. So, is the frictional force any different if the tube is longer or shorter? Good. So we can all agree then that the frictional force is going to be a constant, regardless of how long the tube is, which means there's a constant acceleration here. What could possibly make the distance increase if it's going to experience a constant acceleration? All right, and I have somebody in the chat also trying to chime in. Yep. So this velocity determines how far the box will slide due to friction. So right now, you have to understand, that has nothing to do with the length of the tube yet. Our conversation here has just addressed what it will take to make D larger. We need to have a larger velocity after the collision. So now we go back. What determines the value of this velocity after the collision? Is there anything about the masses that are changing because we changed the length of the tube? No. So the actual collision part, the part that has to do with momentum here, is going to be mv before the collision and m plus mv final after the collision. Now, if the masses don't change, the only thing that can affect that velocity after the collision is going to be this velocity that the dart acquires from the tube. So now we know the connection between the length of the velocity of the dart and how far the box is going to slide. If I make the velocity of the dart greater, the box is going to slide farther. So now I have to deal with what's going to adjust the velocity of the dart when it leaves the tube. And that has to be related to the length of the tube now. And you have a number of ways to address this. You can say that if you have a longer tube, then a constant force will give you a larger final velocity because the acceleration acts over a longer distance. You can say there's more work being done on the dart because the length of the tube is greater, but the force is the same. Thus, a higher kinetic energy, which means a faster dart. But those still don't answer the question. You have to explain why changing the length changes the velocity, why changing this velocity changes this velocity, and why changing that final velocity changes the distance. If you didn't connect all of those dots together, you couldn't get all 4 available points. So everybody who said make the tube longer got 1 out of 4, which is a 1 on the exam. All right, so that's the issue here. Now, you could show it mathematically. It's super straightforward, right? We all know that. I mean, that's got to be true. And that's got to be true. And there, that has to be true. And you can't write any of this, or at least if you are, you have to write it inside a text box. But this is how you would calculate how far it would slide, knowing how long the tube is. I guess I put D here, but I mean the length of the tube there. So connect all of the dots together. You can't acquire all of the points. So in that little sheet there, when we talk about answering a question where a paragraph is required, you must take the reader all the way from the result to the thing that changed. You can't in any way assume that the reader knows physics. So you can't say that increasing the length of the tube does more work, therefore the distance will be greater. You have to connect all the pieces together for them. This next question is, students derive the following equation for the distance. And there's a lot of things there. Obviously, I have this here. We could start doing that work to figure it out. But I don't think you have time for that. 25 minutes, right? You have a choice to make when you see that equation. Do you verify the equation by doing the math yourself, or do you start looking for things in that equation that are likely to be true? So, they say without algebraic manipulation of equations, explain whether the equation accurately matches your explanation in part A. And the only thing that your explanation in part A talked about was whether an increase in length showed an increase in distance. This part of the problem is only worth 2 points. Because all they care about, I think 2 points. All they care about is you verifying that what you said in the earlier part matches. And the only thing you talked about was how the length of the tube affected the distance. They're directly proportional in this equation. And if you guys aren't looking at the equation like I am, this is what they give you. Now, I don't know if that's a solution or not. It probably is, but because I'm seeing this in the denominator, I'm seeing this ratio in the problem, and I'm seeing this in the problem. So it's very likely to be true. But like I said, I didn't solve for it. But I see that if L gets bigger, D gets bigger, and that's the only thing they're asking about. They're not referencing any other variable. So when you're looking at budgeting your time, answer the question they've asked. I've read a bunch of yours. And do you know how many people just said yes? Without any justification. Or the justification, yeah, it was yes. Because the length gets bigger, D gets bigger. You can't say that enough. You got to say yes. You have to give some kind of cognizant explanation related to the equation. In the equation, there's a direct proportion between the length and the distance. So if the length increased, the distance would increase. You can't... Go ahead. Well, saying directly proportional means that it's in the numerator. So my understanding is that you a mathematical term is okay to be used, but let me just give you an idea here about what they said. It was only worth 2 points. So it says 1 point is earned for a statement that includes a reference to functional relationships, that the force or the distance is in the numerator. And 1 point is earned for a statement that as the length increases, the stopping distance increases. So, they're clearly, wanting to make sure that you only get both points if you indicate that the relationship shows that direct proportion. But you don't have to say the words direct proportion. But you do need to indicate how mathematically an increase in distance is directly related to an increase in length. It's only 2 points, but at this point we're at 6 points out of 15, which is breaching the line of passing. So, when we look at how the points are distributed, the justify has to be something where you're not counting on them to make any conjecture on their own, that you are making the conjecture for them. Question C, of course, students then change the force so that it can be described as a function of position. So, by the way, can you name a force that is related to the position? This is where Mr. Shelton quietly weeps by himself, alone in his office, sad, and just in an unhappy, dark place. Yeah, thank you, Hooke's law. That's all we needed. Yeah, this is Hooke's law. That's all that is. The force is proportional to position. So the tube now has a spring in it instead of whatever they're using to push on a dart. That's all it is. And don't make it more complicated than that. It says students change the force so that it can be described as a function of position. So the force equals 12x. Explain how the students could use the equation given above to find the launch speed of the dart if the length of the tube is 2 meters. Now, they gave numbers. Are they looking for a numerical answer? I don't think so. On the other hand, do you understand the implication of changing the force to be proportional to the position? Because I think there's a lot here. And I think this is where the true physics comes in, because they're asking for an explanation that recognizes that the force is no longer constant, that the force is proportional to position. So your whole basis, or at least the basis that I gave just a minute ago for how to deal with this problem, was to deal with the fact that if the force was constant, then the work done was just F times L, which is no longer true. This is no longer the work done. The work done would have to be 1/2 12x squared, because that's the energy in a spring. I'm not integrating it because I recognize Hooke's law. And hopefully Matt, who answered in the chat, also recognizing that it's Hooke's law, would know this is the amount of work done for a force that's proportional to position. If not, then you might have to go the route of proving it to yourself. To figure out the amount of work. And it's definitely going to be harder to do. So they're not asking for a numerical answer, by the way. It just says explain how the students could use the equation given above to find the launch speed of the dart. They are looking for you to say that you would have to integrate and then use that to be equal to the change in kinetic energy, and so on and so forth. Well, the 40-minute limit just yeeted us out of class. So